Good morning. Can you hear me? Test, test, test. Hello, everybody. Good morning. Welcome to the early bird session of Learning Control Systems. So we met already last Tuesday. We talked about, we had a preliminary introduction to the hardware platform we're going to use during this course. But today is the first official lecture of Control Systems 2, so we will do it by the book and start with the introductions. So my name is Jacopo Tani. I am a Ober assistant in the institute, in the Frezzoli lab of the Institute for Dynamic Systems and Controls. My background is in space engineering. My PhD in aeronautical engineering and in particular control systems. I spent my PhD years doing research on image-based control, and in particular studying the problem of motion blur. I then moved on to doing a postdoctoral experience at the Massachusetts Institute of Technology, where I worked on developing a payload for discovering alien life on Mars, together with Harvard Medical and NASA. And I joined ETH 6 months ago. And this is my first proper course, first course with so many students, and I'm very glad to be here. The lead assistant for this course is going to be Claudio Ruch. Unfortunately, he is not here today. Claudio is a PhD student in our lab, and his research verges on autonomous mobility on demand. This is a very big course. We have more than 350 students enrolled, and the logistics behind it are non-trivial. In order to make everything possible, the real hard work that goes on behind the scenes is done by our team of teaching assistants, which I would like to introduce. So, Joella, could you come up first?
So, hi, everybody. My name is Giulio Zardini. I am a master's student of mechanical engineering in Frezzoli's lab. And in this lecture, I will be preparing the lecture notes. I will be part of the team which writes the exercises you will solve in your recitals. And I will be part of the people who actually hold the recitals. So we have many other TAs. I can ask you to come here so you can present. Everybody will have a different task in our big picture control system course. So, Julian.
Hi guys, my name is Julian Kindle. I'm currently in the last year for my bachelor for electrical engineering, and I was doing a group work on Duckytown last semester, and therefore I'm a teaching assistant for the hardware exercises.
Hi, my name is Lukas Spanagel. I'm in my 6th semester of a bachelor's degree in engineering, in mechanical engineering, and I'm currently doing my bachelor thesis on iterative learning control at the IDAC, and I will be one of the teaching assistants for the hardware exercises as well.
Good morning, I'm Philip Barm. I'm also in my 6th semester of my mechanical engineering bachelor. I'm doing a focus project in robotics, and together with Julian and Lucas, I'm going to work on the hardware exercises.
Morning, everybody. I'm Philip Banninger. I'm also in my 6th semester at bachelor, in my bachelor program in mechanical engineering. I'm doing a bachelor thesis at IDSC as well, and I'm going to do the theoretical exercises. I'm going to help you solve the exercises.
Good morning, everyone. My name is Eugenio. I'm a master's student in the first year, and I've already done the control system teaching assistant last year. So I'm looking forward to have a great time with you this year, too.
Hi, everyone. I'm Gianmarco Bernasconi. I'm in my 6th semester of Bachelor in Mechanical Engineering with my focus vertiefung in mechatronics. And I will be responsible for the hardware part of the course with the Duckytown platform.
Hey together, I'm Ben. I'm also, as Gianmarco said, responsible for the hardware, so to be sure that all the Ducky bots are running this semester. And yeah, I'm a master's student in Frezzoli's group, working on Duckytown. and I'm also responsible for writing the exercises together with Julie.
Good morning. My name is Laura Guarini, and I'm a bachelor student in mechanical engineering, and I'm going to hold one of the exercise classes.
Thank you very much. And Zenan Lapandic will be a TA as well. He'll be focusing on the software exercises, and unfortunately he can't be here today either, but it's worth mentioning. So regarding the rooms, lectures are going to be held in this very room, and the whole lecture is going to be live streamed in MLE12, where we have some of your colleagues that are following us. Thank you for being there. And as we mentioned, we're going to have some optional lab activities. So we'll call lab the spaces where you will be able to go and play around with the hardware and do tests. The labs are MLF 44.2 and MLJ 44.4. Office hours will happen in the labs for the TAs, and in the MLK 37.3 for my office hours. The times of the office hours will be determined and communicated in the next week. So in this year's course, we will be producing slides and lecture notes that will be uploaded on the site of the course. The slides, we will try our best to make them available by the beginning of each lecture, while the notes will come up with some probably 3 or 4 days delay. They will come up before the exercises sessions related to the lecture on Friday that happen on the next Tuesdays. In addition to these notes, we will refer to the control systems textbook of last semester's course, Control Systems 1, especially for the first lectures. And we'll use 2 other books, Multivariable Feedback Control Analysis and Design by Scottis, Gatt, and Postlethwaite, and The Essentials of Robust Control by Kevin Zhao. These books, it's not necessary for you to buy them. We will point out some chapters and relevant paragraphs as we go, and we will either make them available through the notes, or you can find most of these texts online as well. So grading, as far as grading goes for this course, the full grade can be achieved through the final examination. There is going to be a written exam. And as we have discussed, there are going to be optional hardware exercises that will count for up to half a point, a bonus half point on your final grade. We will still, we were thinking about what is the best way to map the exercises and the final bonus. There might be a competitive aspect. There might be more of a check-off approach. You go through a script and you perform some experiments to satisfy some conditions, and some TA will verify that you have done the work. But this will be determined in the next weeks as well. So as far as question goes, we are a lot. So I would like to discourage as much as possible the use of emails and one-to-one question asking, because every time you ask a question to one of us in particular and we give the answer, we're losing the opportunity to answer that question for everybody else. So it's efficient to use a piazza, this forum, where you can post your questions and we will answer, and everybody will have an opportunity to see what is going on. So use a piazza as much as possible for your content-related questions, and try to get in touch with me or the TAs only for maybe personal matters or things that shouldn't go on Piazza. So I smiled this morning when I was looking at the responses, some of your responses from the preliminary questionnaire that you have filled regarding your expectations for the course. So I tried to make a brief summary, and I divided them in 3 different groups. The first group is the one that will probably be able to do something about it. The second group is the one that it's a little bit more tough for us to promise anything. We don't make guarantees. But the third group is unfortunately not something that falls within the domain of this course. I guess that we might be able to give you pointers, but you might want to come and talk to us in person if that's the situation. I'm referring, of course, on learning how to control my life. So let's start from a little bit of context here. This is an attempt, by no means comprehensive, to try to give a big picture overview of what is the field of controls, what are the typical problems, and most importantly, to stress what should you already know, that is, what did you do in, what did you treat in the course of Control Systems 1, and what instead we will be focusing on in this course. So typically, when you have to design a controller, you're facing a challenge of controlling a system, you have seen the importance of modeling, right? Typically, actually, controls classes are, especially the introductory ones, are called modeling and control, because without modeling, it's really tough to do proper control. And the different ways in which you can have, I mean, there are many ways of describing a model of a system and formulate it mathematically, but typically either you don't have a model and you're in trouble, you have seen in Control Systems 1, particularly linear time invariant single input, single output systems that are very important because on those lie the foundations of most of the theory that then applies to control in general, even for complicated plans. And you have seen a little bit of how to deal with nonlinear systems. Nonlinear systems are most of the real systems in the world, unfortunately, I would say. There are procedures to deduce a equivalent linear system under some asterisks once you have a nonlinear model of a system, and then reconduce basically the tougher problem to the simpler one for which we have a lot of results. And I'm referring to linearization. In this course, we will look at multi-input, multi-output linear time invariant systems, which sit somewhere in between in complexity between SISO systems and nonlinear systems. And we will not talk about linear time varying systems instead. So once you have a model of a plant model, you really need to sit down a second and think, okay, I need to define a controller. I need what am I doing it for? So the umbrella names for the objectives of controllers, which is something we'll look in detail today, are stability, performance, and robustness. And robustness is often referred to robustness of performances and robust stability. In Control Systems 1, you focused mostly on stability because it is of paramount importance. Stability means you don't want your system to blow up, basically. And on performance. So you defined the time domain specifications, frequency domain specifications, and you looked at how to satisfy these in a number of situations. You did mention, you did get an intuition on robustness, but we will, in this course, treat a little bit more in detail the robustness side of things. Because, as we will see, all models are wrong, but some are useful, right? So every time you do a model of a system, you're just giving it a description that satisfies your purpose. You're describing the phenomena that are useful for your specific applications. You are never really describing what's going on. There is always something that is off. And this difference between what the nominal model of your plant is, what you assume the plant, how do you assume the plant to behave, and what it actually does is the main cause of the robustness problem, and it happens pretty much all the time. So once we understand what is it that we want to control, we understand what are our objectives, and we specify them. there is a matter of implementation. So control systems is a very theoretical, if we want, discipline of engineering. But at the same time, it's very practical. We really want to control physical systems. And the aspect of the implementation is not, hasn't been stressed in Control Systems 1. Typical implementations are either analog or digital. Analog means that they're based on continuous time, and most of our analysis, actually all of the analysis you've seen so far, verged on continuous time description, deterministic continuous time descriptions of systems and controllers. But what really happens nowadays, what happens in the Ducky bots you will see, controllers are no longer custom-built apparatus for a specific system, but there are digital microcontrollers that can be programmed to read inputs, send signals that generate through the actuators the inputs to the actual physical system. But everything that happens on a computer goes on not in continuous time, but in discrete time. So in order to understand what are the challenges of this implementation side of things, we will have to reformulate some of the stuff we have seen in discrete time. And that's something that we will do in this course. We will give a detailed description of discrete time formulations of systems actually in the next class. And then, as we go forward to the course, we will, when necessary, when useful, show the discrete time equivalent of the continuous time results we will see. So finally, once one has decided how the whole plan is going to be carried out, how the control system is going to be implemented, then comes the actual question of, okay, but what controller, how do I do the control? What controller approach, architecture, whatever should I use? And there are many, many different kinds of controllers. This list is by no means comprehensive. They typically fall in three big categories. The loop shaping approaches, which we will see today as well, because they are really the classical way to control systems, and they are very useful. Controls has this thing about the magic of the frequency domain. It's so much easier to see things in the frequency domain rather than in the time domain for a number of reasons, because the challenges are more easily seen, so from an analysis perspective. And the math is easier because it turns out that when you have interconnections of systems and you study them in the frequency domain, simply literally the convolutions become multiplications and things like this. It's easier to look into problematics. Then there are the class of controllers that are based more on time domain signals, so typically on the intention to minimize or maximize some cost function. It could be you want to minimize the tracking error while you keep the energy you spend for your system, so some measure of the input effort low. And there's a family of approaches that come from these considerations. We will be looking at some in this course, especially what go under the name of the H2 and the H infinity family of controllers, the linear quadratic regulators, and the H infinity approaches. And then we'll look, and there's a third family of controllers that is typically more automated and takes into consideration sliding windows of things. The king of it is model predictive control, which is a very effective strategy for controlling systems that have big dimensions, so a lot of state variables and are multi-input, multi-output. We will not talk in detail about model predictive control in this class. There is a dedicated course for model predictive control, which you should attend if you're interested. What we will do in Control Systems 2 is, towards the end, give a little bit of intuition on how to control nonlinear systems directly, because the linearization policy that I have described before doesn't always work well. A linear time invariant system is a very specific thing. A nonlinear system is everything else, okay? So there's some easy nonlinear systems and some more complicated nonlinear systems. And the linearization strategies typically work well in practice only if you have a simple nonlinear system. So just to give a little bit of an overview, in Control Systems 1, this is just to ring a bell and see if you recognize these words and to get a little bit back in the mood, which is going to be the motive of this whole class today. You saw in Control Systems 1 what is the importance of modeling and what are different approaches to do so, state-space representations, transfer functions, ordinary differential equations. You defined the concepts of state, of system, of output. You studied the fundamental properties of linear time invariant systems, such as stability, controllability, observability. You defined control objectives. You defined the tasks of analysis and synthesis. That is, the analysis is once you have, is the problem of understanding. Well, if you're given a plant and a controller, well, does it satisfy the specifications that I want it to satisfy? Well, the synthesis is the inverse approach. Given specifications and a system, how do I figure out a controller that actually satisfies them? Then you looked at effective nuisances, things like time delays, like actuator saturations, right half plane zeros, things like this. And you've discussed a little bit the idea of robustness. This course, as I mentioned before, the main pillars are going to be studying multi-input, multi-output systems, understanding the challenges of robustness related to it, and we'll talk of state-space theory, so how to do controllers based on state feedback, which is a big chunk of controls. This is a tentative schedule of the course. Note that we will have 13 classes instead of the nominal 15 because of holidays happening in 2 Fridays, the Easter ones. We will have 3 lab sessions in the weeks that are mentioned in this part here. And as you notice, we will, at the beginning, recap, then go through some robustness challenges, then we'll look at feedback, as state feedback theory, and then we'll delve into details of different ways to do multi-input, multi-output control synthesis. So what are we going to talk specifically about today? We're going to talk about the control objectives a little bit more in detail. I mean, we need to understand where we're going before setting ourselves in a journey. We will then talk about sensitivity functions, because the frequency domain is something that is really important, and we will describe in some detail what are some really important tools for feedback control for linear systems. And I'm referring to the sensitivity functions and how they relate to the specifications of a system. And then we'll look at what stands in our way. Once we defined what is the final goal, once we defined what are the tools to get there, you need to know what stands in the way, what are the constraints. And so we'll talk about some fundamental limitations to control. So the objective of this first learning module is to recap the terminology, look at what the objectives of a controller typically are, and refresh the intuition on some fundamental ideas. So this is a feedback loop. How many of you have seen this feedback loop before? Everybody, right? This is an easy one, everybody. Okay, so you might have seen something slightly different than this, because but let's go through the loop. What are we looking at? We start by the plant. The plant is the model, that is the process that we want to control, the physical system that we want to control. Actually, the plant receives some inputs and produces some outputs. The outputs are typically not directly accessible for us. We don't see what really goes on. What we see is what we measure. Anytime you measure something, you're introducing some noise, some measurement noise. So there's an additive noise, typically after the input. We can call it a sensor noise. And what we have is a measured output. The measured output is feedbacked to a controller there are different architectures to do this, but the most typical is that of comparing your measured output with what you would like the system to do, which is follow a reference trajectory, which is the signal R. The reference trajectory is compared to the measured output of the system, so the ideal case put in comparison with the actual measurement, and that tracking error is used as the driver for applying some logic based on this tracking error to produce an input that then typically does not go directly in the system, but passes through some actuators, through some transducers of different types, depending on the physical platform we are working on. But they typically introduce something that we call a disturbance, that is an external unwanted signal that perturbs our output. And this perturbs the input, and this perturbed input goes back into the plant to close the loop. There are two big, it's important to understand that there's two aspects to a feedback loop, one that we can do something about and one that we can't really do anything about. What we can't really do anything about is the process, which basically receives as input, it's all that what happens here in this right-hand side, it receives as input the actual input, the output of our controller, and noise from the environment. The plant is typically given as well. It follows laws of physics. We can't change those. So the environment and the process are something that are given to us. We just need to deal with it. What we can think about is instead the controller. This is designed. There are many different ways we can design a controller. What we're showing here is a two-degree of freedom, sometimes called controller approach, where there is the famous feedback block, which we all love. We studied in detail in Control Systems 1. And there's a feed-forward block. The feed-forward block, we'll look at some concepts of feed-forward today, is, let's say, preliminary action that you would apply on your reference. And it turns out that it has some pros and some cons, like everything in life, and we'll look at them later. There are different ways of doing different control architectures. Mostly, you will see that the feed-forward part is not going to be always around, or sometimes you'll have a controller that is not driven by the tracking error, but might have some more complex relationship verging directly on the reference and on the output of the measured output of the system. And don't take this as the feedback loop. Always be careful in understanding what is going on. You will always have disturbances. You will always have noises. You will always have a plant, a controller, and so forth. But not necessarily the disturbances and the noises, for example, will enter the feedback loop in the points where I have shown them here. It is not uncommon to find disturbances that come in different places. So while or noises that feed in the loop in other positions. So there are more general ways to represent a feedback loop, but we'll get to them and we'll introduce them when and if necessary to make our life easier. So what are the control objectives? Control objectives are, as we said before, stability, performance, and robustness. And in order to achieve these objectives, we typically need to work with two different sets of tools, one which we call those of analysis. How do we check if the specifications of robustness, stability, and performances are met given a controller and a plant? And another set of tools that is that of synthesis. How do you produce a controller that does the above? So let's look at these concepts one at a time. So stability is arguably the most important and first objective of any controller. You really do not want a system to blow up. So what does it mean to blow up? Does it really happen in practice, or is it only a mathematical way of saying? There are many ways to define stability. The ones you've seen before, and for linear time invariant systems are the most common, are the concepts of Lyapunov stability, which you can read the mathematical definition by yourself, but the intuition is that if you take a system and you perturb it, you select an initial condition of the states, then you let it go without external forces, inputs coming in and doing anything. The system will have a dynamics that is going to be contained within some bounded region. A little bit more strict is instead the concept of asymptotic stability, which is fundamentally the same thing as Lyapunov stability, but the bounded region is very, 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 very small. It's 0. So in asymptotic stability, you perturb a system, and the system, when you let it go without putting external inputs, ends up back to 0, to an equilibrium position. Another concept, way of thinking about stability is that of bounded input, bounded output. So the idea is if I send a finite amount of energy in a system, there has to be a finite amount of energy at the output of a system. If I send in a bounded input, a system is stable if the output is bounded as well. So if a system does not respect any of these conditions of stability, it's called unstable. What does it mean? It means that if you perturb it, if you send an input, if you put in some condition, its dynamics will make some of its state variables or the output diverge, go to infinity, okay? And while in math we see infinity, in the real world infinity doesn't exist, but in the real world, you typically have a wall or some other physical constraint, and when a system wants to go to infinity, it means it will end up breaking something or breaking itself, okay? When we talk about performance, you have seen there are typically two big problems that are studied in control. One is called the problem of regulation, which is that of trying to determine what is an input that allows you to keep a certain reference, a certain set point for your system, despite the presence of disturbances. So disturbances come in, try to shake you around, but the regulation problem is how do I find out an input that counteracts the effect of these disturbances and keeps me close to my set point. And there is the tracking or the servo problem, which is how do we follow a reference trajectory that is changing in time? How do we devise an input that is such that the system follows a reference trajectory as closely as possible, of course. We will see that the main challenges for these two problems lie in rejecting the disturbances or attenuating the disturbances and the noises of the system, which play a big role, and we will see some detail about this today. So robustness is another very important topic. The idea of robustness is that of things don't really always go as you planned. So we can define robustness as a robust controller is a controller that works well in the sense it satisfies the objectives defined before, even when the plant is different from what you modeled it for. So when a system is insensitive to model uncertainties. And model uncertainties happen in real life continuously because even if you have a very simple physical system that you know the first principles and you can write down how exactly everything works, maybe with time, with aging, with tear and wear, those parameters might change. Think about simple spring on a door. If you use it 1,000 times, the spring won't have the same constant as before, right? So it's if you design a controller for a system with nominal parameters, these parameters will have bounded variations over time, but your controller that was designed for the nominal condition still needs to work for all the possible bounded variations, all the possible effects of these bounded variations. That's called a robust control. Or other typical causes of model uncertainty come from poor system identification, basically. So system identification, who knows what system identification is? Nobody ever heard the word system identification? Okay. So system identification is the process of figuring out the model of a plant. So say you are an engineer working somewhere, you want to reverse engineer, you have a piece of hardware that you don't know how it works, you want to write some equations on it, about it, that describe its behavior. There are systematic procedures for determining the model of the system based only on inputs and outputs, so on the knowledge of the input you send in and the measurements of the outputs. So this is very typical. System identification is done continuously, but there are some conditions in which it's difficult to do good system identification, in particular when there are high-frequency behaviors that are difficult to stimulate. So typically when you do experimental system identification, high-frequency behaviors are badly modeled, so that's a source of model uncertainty. Or when you're dealing with plants that are inherently open-loop unstable, that makes it tricky to do experiments on them, because if you do something wrong, everything blows up, so the model uncertainty tends to be a little higher in those situations. We will talk about robustness, stability, and performance later in the course, and basically these are the two problems of making so that the controller designed for a nominal plant works even in the worst case scenario for stability and for performances. And when I say worst case scenario, it means of all the possible variations there are in a system generating a family of different curves, we'll go pick the ones that are we like least, and make sure the controller works for those situations. So what tools do you know already for analyzing and synthesizing controller? For nominal stability, you've learned some fundamental tools, some approaches that are really important. If you don't remember these things, if these names don't ring a bell, go check them up. So, in particular, the root locus approach, Bode diagrams, and the Nyquist plot, the Nyquist criterion for determining stability of systems. These are all very powerful methods. They all have some things in common, in particular the fact that you get to understand the behavior of the closed-loop system based on the analysis of the open-loop transfer function of the system. That's good, as we will see later, because it gives more insight on how we can modify our controller to do stuff. And it's probably worth noticing that the Nyquist criterion is the one that is more powerful. It works in the broader class of cases, so it's the tool we will be using most. Bode diagrams are functional to writing Nyquist plots. At least they provide some intuition to make Nyquist plot drawing easier. But they describe the frequency response of a system. And there are some fundamental concepts about this frequency response that we will look as we go through this lecture today. And basically, they represent the magnitude and the phase of a system, of the response in a system. And then you looked at tools for stability, for robustness, which are, you looked at nominal performances. You defined the time domain specifications, frequency domain specifications. I'm thinking about, let's say you have a second order system, you want the rise time to be less than a certain number, you want the settling time to be within some time interval. You would like the overshoot not to be too big. These are examples of time domain specifications, which you've seen in Control Systems 1. And there are frequency domain specifications that are related to, okay, we saw that to control a system, you want to design a performant controller. What you really need to do is you need to try to be insensitive to disturbances and noises that come from sensors and actuators, from the things that actually make your controller work in practice. You have seen that it is possible to do loop shaping. You looked at these lead and lag elements that basically are approaches for you to design, shape the frequency response of a system and obtain desired properties in specific frequency ranges. And then you looked at some tools for robustness, in particular the margins, the phase margin, the gain margin. You were told that you can look at them in the Nyquist plots, you can look at them in the Bode diagrams, and they represent a measure of robustness in the sense of how much can you modify the gain of your controller before things go unstable, how much can the phase of the system change until your system goes unstable. So there are measures for that. As far as synthesis, what happened? As far as synthesis goes, you have studied in particular two ways to design controllers. Loop shaping, as I mentioned before, it's very powerful. It's the fundamental family of controllers. We will talk about some loop shaping today. And then PID control, the blessing of controls. You will see that PID is at a sweet spot of being easy to use, easy to implement, easy to understand, provides decent performances, can be tweaked until death is typically the technical term you use to find the coefficients to make things happen well. And you studied PID control, and you saw how you can obtain some desirable properties of systems by the combined use of these three terms that affect the tracking error. So, since loop shaping is really the fundamental way to do controls, and it sheds a lot of insight on what are the problems that are happening, we will dedicate the next part of the lesson to look a little in detail at what does it mean to do loop shaping. What time is it? So are there any questions? There are 4 minutes before the break, so probably we shouldn't start a new module. Questions, comments, doubts? Feel free to ask questions. And even if we are in live TV and this, whatever you say will stay around forever and ever, don't worry, don't make this pressure you. So, questions? No? Okay, so we can take a break now, and we will start back at the end of the break. Can you hear me? Can you hear me? Yes, you can. Okay, welcome back. So, we left at saying how useful it was to do loop shaping, and because it allows us to address many fundamental challenges in achieving performant controller design, and makes our life easier in doing the computations. So we'll talk about sensitivity functions in this next 20 minutes. Sensitivity functions are transfer functions that map the relationship between different inputs and outputs of the feedback loop we saw before. And so before we get into the details, it's maybe worth recalling this fundamental concept of controls, which is that of transfer function. What is a transfer function? Transfer function is a map in the frequency domain, the Laplace domain, between two signals. And typically, when we say just transfer function, it's kind of assumed that we're talking about the transfer function between the input and an output of a system. But actually, a transfer function can be defined between any two signals. So why are transfer functions useful? They make analysis easier. So it's easier to see the problems of disturbance rejection and noise attenuation in the frequency domain rather than in the time domain. And why? Because for two reasons. First, because the math is easier, and then because there's this key idea that you might have seen in, you definitely saw the key idea of how do sinusoids or sinusoidal signals propagate through a loop. So say we have very simple loop, okay? We have an input that goes through a controller, of which we represent the transfer function as C of S, that, we get some signal here, let's call it, doesn't really matter, A. Output produces an input that goes into the plant, which is the model of the system, and produces an output. We take this output,
Mr. Tani?
Yes?
Could you write a bit bigger, please?
Bigger?
Yes.
Bigger than this?
Yeah. Thank you very much.
Easier said than done, huh? Okay, I'm ready. So, attention please. Say we have a signal that we call A that goes inside a controller of which we represent the transfer function of C of S. This produces a signal as an output, which we call the input to our plant. And there's the transfer function of the plant, which produces a system output. Okay? This is like open loop. We feed back this output through a negative feedback, which is very typical, and we ask ourselves, what is this signal B? And what is the relationship between B and A? So we're not hooking up anything here at the moment, okay? So the idea is that if we send, this was the fundamental consideration that Nyquist did that led to the Nyquist condition and the Nyquist criterion. If you ever wonder, what happens if I send a sinusoidal signal throughout a system? How does it change? How does it propagate in a loop? And however it propagates, we know that it's going to have some variations in its magnitude and phase. And the signal B is going to be another sinusoid, because we know that for linear time invariant systems, when a system reaches a steady state, if you send a harmonic input to the system, then the output will be a sinusoid at the same frequency, but at different magnitude and phase. And actually, the mapping of these magnitudes and phase represents the exercise of figuring out the frequency response of a system. So this B is going to be somewhat of a sinusoid as well. Now, the idea is, if I start tweaking around the parameters of the system, for example, the controller, this sinusoid somewhat will change as well. No, it's going to stay at the same frequency, actually, but it's going to change as well. Okay, in magnitude, maybe it's going to change in phase. So if you ask yourself the question, for what combination of parameters does the signal B, is the signal B equal to the signal A? These could be seen in time or in frequency. Because when this signal is the same as this one, then I can just bridge the loop, hook it up, and the system will self-propagate forever. There's not going to be anything that changes. It's going to be a marginally stable condition. Well, but the signal A, the signal B is what? Is, well, minus y, right? Because y, this is minus y, and signal B is minus y. And y is equal to what? It's equal to P U of S, right? But U is equal to C of S times the signal A. No? So if we want this, so this is what you might recall is called the loop transfer function. And if we make signal A sinusoid, as we said, then this function, let's say it's a sinusoid at some frequency omega 0, this is going to be the transfer function evaluated at that frequency. Now, if we want the signal B, we're looking for what condition needs to be satisfied such that this signal here is the same as the signal there so that we can hook it up and it continues forever. Well, B has to be equal to A, right? So this has to be equal to A. And it's a way of saying that, there's a minus here, so signal Y has to be minus A. So this leads to this condition that some of you might recognize being the stability condition in the Nyquist plot. If you always want the open loop response to your system to stay away from the critical point, -1, because if you pass that, then what happens? The signal in B is a sinusoid that is bigger than the signal in A. So this will lead to an amplification in time of these sinusoids, because that's how harmonics propagate through systems. If instead you are within the unit circle, if you're far away from the point -1, then this signal will be attenuated, and therefore you'll tend towards a stable condition. This is a very powerful idea. So transfer function allow us to evaluate the frequency response of a system. That is important. It allows us to understand concepts of stability. Math is made easier, and even the synthesis is made easier, because by looking at frequency transfer functions, we can reason on the effects of the open loop transfer function on the performances of the closed loop system. And you saw this continuously with the root locus, with Nyquist. And why is that useful? Because, I need to get out of the way. Because the open loop transfer function is just C times P, where C is our controller, while the closed loop transfer function is this mess. So if we ask ourselves the question, but what is the effect on, because at the end of the day, what we care about is the closed loop performances, right, after we apply our control. But it's easier to see the effects on the controller, on the closed loop stability, closed loop performance and stability, by just looking at the product of two functions rather than looking at this more complex relationship. So it makes even synthesis more intuitive. So before moving on, some really basic recaps on some properties of transfer functions. Given a system like you've seen many times before, a linear time invariant system expressed in the time domain, the output is characterized uniquely by this function. And in general, and this is a time domain representation, of course, of the evolution of the output. There is a part that depends on the initial conditions on the system, while the second one is the forced response, and it depends on the input that comes in time. This is the famous nasty convolution integral that tells us how the system in time evolves, that is nicely replaced when we go in the frequency domain. And if we look at transfer functions, this is the ratio of the output to the input in the Laplace domain. You typically get a polynomial like this, a rational function, and this is a complex number for single input, single output systems. And we call zeros the values of the S that make the transfer function equal to 0, have 0 value. So typically, if we think about strictly proper systems, so when the D goes to 0, D is 0, this corresponds to having the numerator, the values of S that make the numerator of this go to 0. And the poles instead are the zeros of the denominator of the transfer function, okay? So here it's a nasty coincidence that a 0 is a math term to represent a solution of an equation. Now, the 0 is the value of the number that if you plug it in, you satisfy the identity, therefore you get a 0. So a 0 of the denominator, we call it pole. Please don't confuse it with the 0 of the transfer function, which is a 0 of the numerator of the transfer function. So the denominator of the transfer function is even directly deducible from the system matrix, because it's the determinant of the characteristic polynomial, and this is good to know. So at this point, we are hopefully convinced that transfer functions are the way to go, and that they tell us some interesting things. Now, we have to think about what are the important transfer functions, which ones are the ones we actually care about. So we step back a second and look again at the loop. So as you see, we have the process here, and we have the controller there, okay? The process receives as inputs the input to the control. So let's look at the whole system first, process plus controller. What are the inputs to the whole game? We have a reference signal coming in here, we have a disturbance, we have a noise. These are exogenous signals. They come from outside. Then we have inputs to the controller, which are to the process, which are the output of the controller, and the inputs to and noise and disturbances, while the inputs to the controller side are the measured output and the reference signal. So the inputs to our system, now that we're hunting for significant transfer functions, are going to be the reference, the disturbance, and the noise. While all the other variables, tracking error, the input, and so on, they're going to be dynamics, of course, of interest, and they're going to be affected by these inputs. So if we do some math, it is relatively easy to see that we can express the relationship between these inputs and the different outputs as some combinations of the transfer functions, okay, of the single blocks. Now, one signal that doesn't appear here in the graph, but is really important to us, and arguably it's the most important signal that we care about because it speaks about how good we designed a controller, is the actual error, which is not the difference between the reference and the measured output, but it's because the measured output is not the real output of the system. It's corrupted by noise, which is an artifact that comes in because of the measurement process. We really care that the system is doing what we would like it to do, that the real output of the system, eta, follows the reference. So if we define this real tracking error as r minus eta, it is relatively straightforward to do these passages. Let's look at them. So let's try a different thing. Okay. So let us look at a reference signal that comes through a feed-forward term and produces a signal that is compared to the measured output to produce an error that then goes into a controller. The output of which is affected by a disturbance. So this is the signal U, this is the signal V. The disturbed input goes in the plant to produce the real output eta that is corrupted by noise and produces Y, which is the measured output. The measured output is then feedbacked to the system, to the input. So what do we want to know? We want to investigate what is the relationship, the transfer function between what we would, let's say the evolution of an error that is not the tracking error here, because this is the difference between the pre-processed, let's say, reference signal and the measured output, but we really care about the difference between the reference and the real output of the system. This is Y minus noise, basically. So let's see how this works. Let's give a name to this quantity. Let's call it epsilon. So how does this go? Well, before we do this, and I am cheating a little bit, it is useful to look at what is the expression of E. So E is equal to what? Is equal to this signal minus this signal. FR minus, can you read down there? No? Really? Okay, let's make it bigger. Let's make it bigger. So E is going to be FR minus YM. YM, so how do you typically do these transfer function things? You start from where you want to, and then you proceed backwards until you get some expression. So what is YM? YM is Y. Sorry, this is Y, not YM. YM is equal to eta plus N. Okay? But eta is an ugly way of saying what? Eta is the input times the transfer function. Actually, the transfer function applied to the input V plus n, which is always the signal as before. So this, we put it like this. Then, where are we heading here? We need to know what the signal V is, right? So the signal V is what? The signal V is U plus D, right? So this is FR minus, let's put the N part, so we take it out of the way, and then it's minus P of S times V. V is U plus D. But U, I'll jump a passage here, is equal to EC, CE, right? So C of S times E plus D. Let's not forget D. Right? Point out if I do mistakes. I'll do lots of mistakes at the blackboard, sometimes even to test if you are careful. So make sure. So at this point, what are we doing? At this point, you see, we have a little bit of a conundrum here because we are trying to find a relationship between the different inputs to the system that are the noises, the disturbances, and the reference, and how they affect the evolution of this tracking error. But we have on both sides of the equality the tracking error, so let's take care of that. This means that we have E there, we have minus PSC, minus PCE here. So we take this part, we slam it on the other side, we get 1 plus, please don't hate me, I will start ignoring the dependencies on S because it's obvious from the context here that we're talking about transfer functions. PC times E equals to what? Equals to FR minus N minus P times D. Okay? So we're getting somewhere. Now, note that this is a scalar, this is a scalar, this is a scalar. So these are all numbers, right? So we don't have to worry about weird things apart from it has to be different from 0. But what I can do is can divide in both sides, but we will do it by pre-multiplying left and right side of the equality by the inverse of that function so that we start getting used to a matrix approach to this stuff. That will come useful later in the course. So we have E. So what I'm doing here is I'm multiplying left and right by the inverse of this. Here I can't fit it, but that's the idea is as long as we do the same thing on both sides of the equal, of course, it's legit. So E is what? Is, what order do we like? Let's put the order as it is. 1 plus PC inverse FR minus 1 plus PC inverse N minus 1 plus PC inverse PD. Okay? So this tells us, if I send in, suppose I have 0 disturbances, 0 noise, how does a change in the reference affect the tracking error, right? So how does it affect it? Well, this has to be, of course, a Laplace domain representation. You do the Laplace transformation of your reference. This is the transfer function between E and R. Let's say we call it H of ER, okay? So reference to input. Doesn't really matter. I'm just not going to use it anymore, but to just express that these terms regulate the effect that the different inputs to the system, which are, as we said before, the reference, the noise, and the disturbance, how they affect E, the tracking error. But that's the tracking error that is calculated by keeping the noise in the loop. What we really want is that the system what we really would like is the real error, tracking error expression. So what is this? We follow the same exact approach as we did before. It's a reference minus eta. What is eta? It's reference minus eta is equal to PS, I'll not put the S's, to P times V, right? But V is equal to U plus D. This is equal to what? It's equal to R minus P. U is C times E. And D is just D. There's nothing we can do about that. But what we can do is we can take it out of this parenthesis. Okay? Now you know why I did that calculation, because we needed the E here. So this is equal to what? Is equal to R minus PCE, which is that long expression. Let me see if we can make it a little bit simpler. So I'll call this variable here, which appears over and over. For the moment, let's pretend it's something called S without getting into any detail, okay? So what's going on here? Minus PC times E. E is S FR minus S N. Is it minus? Yes. Minus S P D. Yeah. So here, then what we have to do now is we have to re-express these terms. And we just, at this point, you got the gist of it. What we have to do is we have to re-express S as that big mess and do the last passage. And the result is going to be the nicely, neatly written one. Up there. So this up there is the relationship between the different inputs to the whole process and the real error. If we follow the same approach by picking any one of the other signals that are in the loop and ask ourselves, what is the relationship between the inputs to the whole deal and these internal variables, which could be our input, it could be the measured output or the real output of the system, it could be the tracking error dynamics. These are all very important quantities. A very common mistake that is done, or let's say thing that is neglected, not given due importance, is that you say I've got a good controller when my tracking error goes to 0, or when I don't know, something related to the output doing what it should do. Okay, that's definitely important, but it's a part of the story. It's important even to look at what are the dynamics of the other variables that make this possible, because if in order to keep your output following your tracking error, your reference signal, you have to use an input that goes to infinity, that's clearly not a solution, right? So following the dynamics of the internal variables is important as well. So do you notice that thing that there's 1 over 1 plus PC pretty much all over the place? There's a lot of repetitions. There are some common terms here. This, of course, means that y is equal to this times this, plus this times this, plus this times the row times columns, right? So what can we notice? We notice that there are lots of terms that are similar all over the place. So we do a little substitution. We say, without putting too much thought into it at the moment, we say, okay, let's just define these six transfer functions, okay? These are so famous that they actually have a name. It's called the Gang of Six, okay? And they represent all the possible transfer functions that there are in a 2-degree of freedom architecture. That is the one that has a feed-forward part and the feedback part. And if we just go back and rewrite these things in the equations we had before, we're just substituting in here, we will notice that we have this nice behavior. So basically, the transfer function S and T somehow are predominantly show up in the relationship. It's the third column, so they predominantly show up in the relationships between the noise and these variables. How does the noise affect these variables? There's S's and T's, and the P of S kind of shows up more in the second column. The F's show up all in the first column, okay? So the feed-forward part influences only the reference, of course, because it doesn't feed back in the loop. And P of S, P times S, is the relationship between the disturbance and the various variables here of interest. So to understand what's the effect of feed-forward, now we'll take a step and simplify things a little bit, because here we're using feed-forward and feedback. And for reasons that will be clear in a couple slides, we will drop the feed-forward part, even if it has, in general, its advantages in some situations. So we have to understand a little bit about feed-forward first.
Mr. Tani?
Yes.
Could you go back one slide, please?
Yes.
Is my understanding correct that if we have a big T of F, that the output of the plant, well, the reference tracking is very good for the output of the plant, but on the other side, ETA is also very much influenced by noise. So if you do a good reference tracking...
you're sort of telling the story of the next 10 slides, yes. That's where we're heading. Re-ask this question at the end of the next 10 slides and see if it hasn't been answered. But yes, you're very right. The bottom line is that there are... of course, trade-offs to be made. It's not possible to achieve everything we want through a simple choice of these functions, even because not all these functions are independent. So there are constraints that apply. And this is a fundamental limitation to how we can mitigate the effect of disturbances and noise in general in the whole system. But this is a spoiler, so let's talk about it later, please. So let's think about feed-forward for a second. So I will ask you a question, and I would like really for some of you to try and give it a shot. And it's a very simple question. How do you make a brick wall fly? You want an answer? No. How do you make a brick wall fly? Come on. We're engineers. It's like, if somebody has to do it, it has to be us, right? So we need to think about it. Any suggestions?
Small TFS noise rejection.
Nobody really wants to guess. Yes. We attach it to a drone. That's a good first shot. We would need many drones. Suppose there's a very big and nasty and heavy wall. But yeah, okay. Or let's try a more engineering approach, right? That's very practical. Let's find a big robot that takes the wall and throws it in the sky. That could be another approach, right? But let's try to be, engineering at the end of the day is making the theory and the practice agree, right? So let's try to look at the theoretical side of things a little bit as well. How do you make a brick wall fly? Yes, sir. I start liking that, yes, reductionist, I like it. You bring it down to the little pieces and you make them fly individually. But that might require a significant cost, right, in the input. You need to hire the people to break down the wall, and each brick has to fly with an independent thing, and then you have to put it back together. So another way of doing it is just you divide it by a brick wall so that the brick walls cancel out, and you multiply it by an airplane, okay? In this way, you got an airplane and it flies. So this is the essence of feed-forward. Feed-forward, well, feedback is something that is based on the measurement of an error, right? So you have your system, you made your assumptions, you made your modeling, you have your external unwanted, undesirable behaviors, such as disturbances and noise that act in the system. And the feedback part operates driven by the error, right? So while you cannot make things perfect, it's very useful, as we've seen, to mitigate these effects. Feed-forward, on the other side, requires a prior knowledge of what is going on. Because if you know exactly what your wall is, you can divide it by a wall and multiply it by whatever you want and make it be whatever you want, okay? This is the key idea of feed-forward, and it's the concept of plant inversion. as long as you know your plant, and let's do a simple example about this, which is really simple, but it gives the idea, maybe. Let's just do it there, but I need another. Let's do it here. Very simple. Let's say we have a, let me see, what is the, so let's say we have literally like just a plant, okay? A plant that has its input and the output, okay? How are they related? Well, the output is equal to the plant times the input, okay? Now, say that I want to find out the ideal controller, the perfect controller, the one that makes everything happen perfectly. Which one is it? It's the one that allows us to follow a reference trajectory at every time instant, okay? So something, let's find the u such that y is equal to r all the time. How do we do it? Well, we just plug in r here. Let's forget about the dependencies. Equals pu. So what's the u that allows this to happen? Well, you just left multiply by the inverse of p, here and here. This goes away, becomes an identity, and therefore u is equal to p inverse r. If we just plug this in here, what we get is that y equals p times p inverse r. This goes away, boom, you've got exactly what you want, right? So plant inversion is really, really a powerful deal. If you can invert a plant, there is no need to do anything else, because you can just substitute what it is and put back whatever you want. Okay, you can make a brick wall fly. So why is this not done all the time? Why does it even exist, the discipline of control engineering? Because this is not possible for a number of reasons. First, I mean, it's not that it's not possible. It's not easy to do, and there are many, many, many situations, most of them that are practically very relevant, that don't allow this to happen. In particular, you need to suppose that your plant P that you want to do the inverse of has right half plane zeros, okay? So unstable zeros, you do the inversion, they become unstable poles. You can't put a controller that is unstable, it will drive everything out of the window. What if there are time delays? Well, if you do an inverse of a time-delayed plant, you're basically saying that you need something that predicts the future. Not going to happen, so you can't do it in that case. What if the plant has more poles than zeros? You do the inverse, well, then you have an unrealizable plant that you can't make in practice. What if simply, as we mentioned before, you have model uncertainty, right? And that sort of happens all the time. Well, if you have model uncertainty, if you do the inverse, then you are not really doing the inverse, right? Because inverse works if you know exactly what's going on and things cancel out. If they don't cancel out, then there's no point. So these are all reasons for which the feed-forward part is something that is useful. It's powerful when you have knowledge of either your disturbance or your reference or your noises, depending where you put the feed-forward part in your loop. But ultimately, since in this course we are going to deal a lot with robustness and model uncertainties, we will just neglect it for now. And the way we do so is by looking at the putting f equals 1 in the equations. So what we get is basically 4 of these transfer functions out of 6, which is the gang of 4. These are really important, and we call them the sensitivity function, the complementary sensitivity function, the load sensitivity, and the noise sensitivity. So these two answer the question, so how do disturbances affect the output? Now, and if you look, in fact, it's the P of S happens between the disturbances affects the output, the real output, and so on. This instead is how does the disturbance affect the input? How does noise affect the input? Because noise really typically is like fast varying, and if it affects the input a lot, you get an input to your system that jiggles up and down very quickly. This typically is a practical problem because causes wear and tear in your actuators, so it's not good for your input to be bouncing up and down. And the transfer function between noise and input is regulated by this part here. You can see noise input, here C of S. These other two functions are really important instead, the sensitivity and the complementary sensitivity. And let's look at them a little bit more in detail. So I've noticed that I'm running really late. So
sorry, I don't want to run you into delay, but we have a question.
Yeah, but I have 5 minutes. Okay, ask your question.
I think it's an important
Go.
question. And on the previous slide, we learned in control system 1 that a small complementary sensitivity T of S causes noise rejection. Is this correct?
Depends how you write your loop.
Okay, with this loop is okay.
With this loop, these are the transfer functions.
Okay, but what I don't understand is if a small T of S is good for noise rejection, why, if I look at my output Y equation in the matrix, so if T is small, this means S will be large for this.
We didn't get to that yet, right?
Okay, so I will ask the question next week, maybe.
Or maybe next a few slides, but
okay.
So where were you? Here we go. So the sensitivity function is a measure of the. It's a relative measure of how much does the transfer function between the reference and the output, which is what we care about. When we change the reference, we want the output to follow the reference. How much does it change due to model uncertainty? Okay. So if you perturb the transfer function by some parameters in the plant and you crank through some calculations, you get exactly S. Okay, so S is called the sensitivity function because it measures the sensitivity of the transfer function between reference and output under variations on the model parameter. So it's really something that rings with the concepts of robustness, okay, because variations in a plant, how do they affect the system? The complementary sensitivity is owes its name to the fact that it's complementary to the sensitivity function. Like if you sum them up together, S plus T, at every S is always equal to 1. And this ties up with what Joella was asking before. You cannot possibly choose at every individual point in frequency arbitrarily S and T. Okay, they have this fundamental constraint. They are one the complementary of the other. If one is high, the other has to be low, and vice versa. Okay. So one thing that is worth noticing is that these two functions depend only on the loop transfer function because PC of S is the loop transfer function that you've seen last year. So if we look at how these functions now affect the thing we derived before, that is the actual tracking error, we will see that what we would like to do is to have good tracking and disturbance rejection. These is like we talked about performances before. These were the problems. And in order to do this, you have to, what do you have to have? So the error, you would like the error to be 0 to any of this. So a small s means that when the reference changes, your error is still low. So it means your output is tracking your reference well. So you want a small s, and this affects the disturbance relationship as well. And if you look at the definition of the S, this directly means that the open loop transfer function has to be high, whatever high means. And instead, to reject the noise, you want to have T that is small, which requires a small L of S. So there is a, how do you say, clash. We cannot, there are contradicting requirements in order to achieve everything. Luckily, these requirements are spread throughout the frequency domain, and this is why the frequency domain shines, because it allows us to distinguish what our problems are and visualize them easily. Because low frequencies are typically characterized, disturbances are typically characterized by low frequency behavior, while noises are typically characterized by high frequencies content. So in order to achieve both of these objectives of disturbance rejection and good tracking and noise attenuation, we could shape the transfer function, the open loop transfer function, to be higher than some obstacle to satisfy the first requirements, and lower than some obstacles at higher frequencies to satisfy the second requirements. This crossover point is very important. It's called the crossover frequency, and it determines the ability. It's basically a trade-off between tracking and fighting disturbances and noises. And one other thing that's not shown in this slide is that the derivative, the tangent at which the crossover frequency happens, at which the loop transfer function passes the 0 dB axis. That's related to the phase margin, so it's a measure of robustness. So actually, the steepness of this function here even tells us robustness. So the whole loop shaping approach is all about how can we achieve these contrasting objectives while maintaining a robust system. You can see many of the things we've talked about in chapter 11 of the Feedback Systems book, which is the book of last year, the Control Systems 1 textbook. Are there any questions? I think time is up, so, but if...